Hi everyone. Today we welcome Antoine Demiquel, who is a postdoctoral researcher who is in the lab since a few months.
Just 1 month, yeah.
Yes, and he will present some of his PhD work.
Thank you for the introduction. So yes, before to start about the real talk, let me to introduce my background. So my name is Antoine Demiquel. I'm a postdoc researcher from 1 month ago at the LVA and LTDS on the supervision of Keren Ege and Emmanuel Gourdon. And I will work, and I'm working on multi-layer structures, and more especially to model some nonlinear interfaces on this kind of structures. And to do that, I'm based initially from the work of Fabien Macchetti and Nicolas Auquier, who are both PhD students in the LVA. So before to come here, I was a PhD student in Le Mans Université, more especially in the LOM, Laboratoire d'Acoustique de l'Université du Mans, sous la supervision of Vincent Tournat, Hugo Thocalis, and Vassos Archelios. So let's start. So my PhD was entitled Control of Nonlinear Modulated Wave in Flexible Mechanical Metamaterials. So first, let me introduce what is a metamaterial. So a metamaterials, I don't know if some of you have some background on this kind of structures, but there are synthetic composite structures that offer unprecedented control over different types of wave. It can be in optics, acoustics, mechanics, or dynamics, for example. And this kind of structure can manipulate wave in ways that traditional cannot. For example, some example of this kind of structure, one of the most classical one is composed of a periodic arrangement of scatterers. Here, for example, in optics, it's a photonic crystal called. It is used for absorb waves in targeted frequency. And in acoustic, for example, we can have the same properties by here, this is a waveguide with a periodically change of cross-section here. And by this periodicity, if we look at the dispersion relations, we can observe a band gap here, the dispersion relation. This is a band of frequency controlled by the architecture where a wave cannot propagate. And for example, also in mechanics, some example of metamaterial here is to control shape morphing. So depending on the geometry of the structures and the excitation here with hand, for example, we can change the geometry of structure. So for my PhD, we are focused in class of mechanical metamaterial called flexible mechanical metamaterial. Flexible mechanical metamaterial can be defined as an artificial compliant structure able to support large local deformations and mechanical instability leading new mode of functionality. As a result, a plethora of quasi-static behavior and function have already been reported with some application to soft robotic or mechanical engineering in general. So here, I display a lot of examples of this kind of structures that can be obtained by 3D printed or by an assembly of beams, for example. Or this is the Japanese art of folding, origami, or cutting with kirigami plates. This is some example of research done in the lab. So here I bring with me a trophy for my PhD. This is a metamaterial composed of Lego. So this is this one. This is a 2D plan here. But this is a chain here composed of Lego. This is cross, more stiff, and some software element here with static finish. If you like to look, this is my device here, and more in general, more recently, the dynamic of this kind of structures in general have shown that the nonlinearity of this system comes from the geometry. And due to that, we can control the propagation and control the effect on the structures by tuning the architecture. So by changing, for example, the shape of the crosses, the mechanical property of the ligament, we can observe different nonlinear phenomena and dynamical response. So in a review in 2021 about FlexM here, several initial conditions, several nonlinear waves and linear waves have been observed For example, in linear and small amplitude, we can observe some linear pulses, wave packets, or harmonic linear waves. Or for larger amplitude, we can observe cnoidal or pulsoid, for example. The idea here is we start for this PhD to study this kind of already known phenomenon and try to go more in details to more unknown things. So for example, with these structures, with Lego, there is already some work on vector solitons, which means this is the solutions, localized structures, which propagate by keeping its shape and velocity during these propagations. Another example already studied is the transition rate. That means there is multi-stable structures. Multi-stable means here we have a chain of structures in gray, blue, and red, different positions. And by adding energy in one extremity, we can change the polarization of the square here to have another configuration of the structures. Another example of things also is cnoidal waves. This is a periodical waves in cross from soliton depending on the coefficients and harmonic solutions. So in my cases for the PhD, we don't see the color here, but modulated wave remains a particular kind of solutions not yet explored. So that's why we study modulated wave. Before to go in nonlinear regimes, we have studied using COMSOL multiphysics some things about these structures. So this is composed of two lines of crosses with some ligament, elastic connections. And by doing that, we have studied the modal analysis of the linear response of our structures. By doing that, we can obtain the dispersion relations, so the relation between the frequency, the temporal frequency and the spatial frequency here. And if we go more in details, we can observe different branches. So the three here, theta, u, and v corresponding to symmetrical modes. So u corresponds to a longitudinal displacement along the x-axis here, for example. Here a shearing mode and a rotational mode. Here, due to the fact the cross are aligned, the modes are decoupled. If we look more in detail at the three other branches, we can observe some antisymmetrical mode. There is a combination between some rotational and other systems here. Now we have some idea of how this system moves, and the idea is to go more in details with nonlinear dynamics. But to do that, we have to go more in details in analytics things. To model the dynamic of these structures, we have work on a lump element approach. That means a mass spring system. So the idea is the crosses are assimilated to a mass, a particle, depending on the mass of the shape and the shape, of the particle, so crosses, square, or something else. And the elastic connection at the middle of the crosses here are physically assimilated by three springs: a longitudinal spring, a bending spring, and a shear spring. And by normalization, we can reduce the parameter here. So we have only one parameter for the inertia coefficients and two for the stiffness. This is normalized by the longitudinal springs. By doing that, also, we need to make some assumptions to find the dynamical the equation of motions. The first one is we suppose all the particles are aligned, so the statical angle equals 0. We consider only symmetric motion on the relatival symmetric axis, so that means we will have only one equation of motion for each particle from one line. So that means we cannot observe on symmetrical mode, but only symmetrical modes. We suppose also we have only 2 degrees of freedom, so that means we kill the shearing modes. We can do that by exciting at the middle of the line. Experimentally, to observe it's a good approximations. And we suppose also the restoring moment just depends on the neighboring particles. And also no losses in the system for the first step. This model was already used to observe pulsoliton, what I presented in the introductions. With all these assumptions, we can obtain these 2 equations of motions here. If we kill the nonlinearity, we can observe directly here the classical mass spring systems here, both for the longitudinal displacement and here for the rotation of each element. This is what we observed. Here, if we compare our COMSOL simulations and our model, we can observe the branch for the rotation and for the longitudinal displacement are well observed. And we can observe here the dispersion relation of the monoatomic dispersion relations, and here another Schrödinger equation. So the topic is, can we observe modulated wave in this field, and how can we model the envelope? The idea here, we have a modulated wave. That means we have a carrier wave modulated by an envelope. But to do that, we need a model. For my presentation, we'll focus on the NLS equations, which is an equations we use to model the envelope of our modulated wave. And we observe some kind of solution of these NLS equations, the nonlinear Schrödinger equations. And to finish, we'll study some extreme wave events. So this is the goal to my PhD. The nonlinear Schrödinger equation is the following. It is a partial differential equation found in various little systems which describe weakly nonlinear and weakly dispersive waves. So partial differential equation because psi here, which is the envelope of the wave packets, depend both in time and space, where p corresponds to the coefficient of dispersion and q of nonlinearity. And depending on the sign of these two coefficients, we have different kind of nonlinear Schrödinger equations. Two variations. So if PQ, the product, is positive, we observe a focusing NLS equations. So that means we have a beam, but due to the property of the medium, the beam keep its shape. But due to the fact of the defocusing NLS equation, if PQ is negative, if we plot exactly the same beam, we observe a defocusing effect, so a spreading effect of our solution. Thanks to these equations from decades, we have some effect observed thanks to this equation. For example, here, this is, I put it here in dynamics, for example, this is called modulational stability. Here, this is an example of experiment. This is a wave tank here, water tank, sorry. We have a wave train here, looks like a plane wave, but due to the property of the medium, a small perturbations will bring some instability. That means the wave train will break and some localized structure will appear, called modulational instability. In optical fiber, for example, we can observe some soliton solutions called bright because the background equal to 0 and a positive value of amplitude go to a bell shape here. And for example, in quantum mechanics or in condensate matter, Bose-Einstein condensate, we can observe dark solitons. This is a hole here, propagating. Or in a mechanical chain, for example, we can observe modulated wave in general. This is the classical example of a couple pendule chain. Yeah. Let me to present to you the goal of this study. So the link between FlexM and the NLS is, okay, we have our equation of motion here, and by putting the ansatz a modulated wave here, so F1, this is the envelope, and here's the carrier wave, we can prove that from this equation of motions, we can find an NLS equation. By doing that, we suppose, first of all, weakly nonlinear regime, so that means the cosine and the sine trigonometric function can be developed using the Taylor expansion here until the first order of nonlinearity. By putting this in the equations, we use some nonlinear methods to build some solution of UN and theta n depending of different order of solutions. But by doing that, we have to put some different scale called multiple scale method, which describes the fast oscillation and the slow oscillation of the envelope by doing that. So here we have x0, t0 corresponding to the carrier dynamics, and x1, t1, x2, t2 to the envelope. And as I mentioned before, our ansatz here, the beginning of the model, is we study modulated wave on the rotation here. By doing that, we can prove from the discrete model equations, we can observe here an NLS equation, we can obtain this one, where P and Q, the two coefficients, depend of the geometry of our structure, so the inertial parameter and the stiffness of the spring. Yeah, we can play with the shape and we can play also with the elasticity. So this is really nice because in theory, if we tune our geometry, we can observe different solutions of the NLS equation in theory. But we have also observed the effect of the coupling between the two degrees of freedom. So what is the effect on the NLS equations? So if P in Q is positive or negative, if there is pin or unpin. So pin, that means each particle are pinned at the middle. So that means all the particles can only rotate. By doing that, we have only one equation of motion for each particles. And we can see that by playing with the coefficient of the stiffness here, the two different stiffness of the plastic films here, and here K is the wave number of the carrier wave, we can observe only the stiffness here, if it's positive or negative, the difference play on the focusing or defocusing NLS equation. But if these times we had these coefficients, if we had this degree of freedom, we can observe the dynamic is more complex. So depending of the geometry and the excitation, here we can observe some focusing and defocusing. So that means for one particular wave number of one particular FlexM, this corresponds to one line here, we can obtain different regime, different NLS equations, so different solutions of the NLS equations and of dynamics and nonlinear effect. So let me show you some example of phenomenon, so modulation and stability and bright and dark envelope soliton in the structures, which was more details in two publications here. What is modulation and stability? As I presented in the introduction, this corresponds to initially a wave train, and due to a small perturbation, we can observe this is a modulation of the envelope, and we can observe locally the generation of high amplitude object. If we look more in detail the spectrum, here what we can observe? We observe K0, which corresponds to the wave number of the carrier. And due to the instability we have in the spectrum here, when the localized structure appear, we can observe here unstable wave number. So here, the localized modulation are observable in the spectrum. In theory, I will go very fast in this slide, we can predict which kind of wave number are unstable. So that means if we modulate, if we perturb our solutions by this kind of wave number inside these branches, where 0 here is the wave number of the carrier, we can treat this kind of modulation instability. And this depends on the amplitude of our plane wave. So by doing that, we confront our theory, of our NL theory, with the discrete system of equation of motion. So what we put initial condition of plane wave and we perturb by a random noise the amplitude to trigger different wave number. So by doing that, we have compared the result when the structure is spin, so only rotations, and unpin, so free, when there is rotation and longitudinal displacement. By doing that, for example, for this blue point, so we fix the FlexM and we fix the excitations. Our theory predicts that there is no instability. Our system is stable, so that means we put a plane wave here. The representation corresponds to n, this is the number of cells here, and t corresponds to the time, so the propagation. So we have our structures, she moved, and we can observe here the propagation. So we observe only a plane wave, and if we look at the spectrum here, we observe only one wave number corresponding to the wave number of the plane wave. If we look this time exactly the same point, but this time the structure can rotate and translate, we can observe here, this is a white area, it corresponds to an unstable area of the NLS equation, what we predict, and we observe here localized structures, both for the rotations and for the longitudinal displacements. If we look at the spectrum, we observe always the wave number of the carrier waves, and around it corresponding to all the unstable wave number. Why there is all this wave number and not only one as for the introduction is because here we excite with a random noise. By exciting by a random noise, we excite all the wave numbers. And what we can observe here, only the unstable wave number, because the stable are not excited. So finally, in conclusion, coupling between the two degrees of freedom can lead the generation of modulation instabilities. If this time we look at the green points corresponding here when it's spin of an unstable wave number here, not stable, defocusing analysis equations, we can observe the formation of the localized structures and also the same for the spectrum, so some unstable wave numbers. But this time, if we take the same FlexM but free, we can observe the system is stabilized. So that means also the coupling between the two degrees of freedom can stabilize the system. If we look now more in details, the free configuration and open structures spectrum here, we can compare directly for a given time the spectrum. So we fix the time and we take the spectrum, and we can observe from the theory here and the numerical simulations, we can observe the match pretty well. And this is for different amplitude of plane waves. Now let's go with bright envelope vector solitons. Let me introduce what is the soliton. And the question is, can we observe soliton solution in this kind of structure? Because we have the analysis equations. We know from these analysis equations the solutions of bright and dark. And can we use it? Can we propagate it in the structures? So answer is yes, but it's not only bright or dark soliton, this is envelope solution. To propagate bright and dark solitons, so soliton in general, we need a perfect balance between dispersions carried by the coefficient P of the analysis equations and the nonlinearity Q. By doing that, we obtain, if P and Q are well defined, we can observe a robust soliton. That means propagate along the space and time with keeping its shape and velocity. This is our goal. By doing that, we have found we cannot only excite initially the rotations. We need also to have the longitudinal displacement to have a good balance between P and Q. This was one condition which is different from modulation and stability. So by doing that, we can also have our analysis equations where G0 and G2 correspond to the function for the longitudinal displacement and our initial conditions. This is a representation of the dispersion relations. So this is only one FlexM and the map, black and white. So finally, for only one FlexM, we can have different area depending on the wave number of the carrier wave, so obtain a focusing or defocusing analysis equations. Here, from the analysis theory, we can have the bright soliton solution here. This is obtained, this is well known. And from our theory, we can find the initial condition we need to propagate it. So this is the shape of the bright soliton, this is the bell, this is only the envelope. And finally, multiply by the carrier wave, we obtain this kind of initial condition for the rotations. And from this F1, theoretical one, we can obtain G0 and G2 following these two relations. And what we can see here, for example, for the case of bright and dark soliton, this is for the bright, the width of the bright soliton depends directly from the amplitude and the P and Q coefficient of our theory. By doing that, we can compare directly the prediction. So the prediction is we solve the analysis equations, and the blue points corresponds to the numerical simulation. And what you can observe is fit pretty well, and the same for the longitudinal displacement. This is for the rotations. If we go faster, this is for 10 nonlinear lengths of propagations, and we can observe it keeps its shape pretty well along the time. If we look more in details here for the 3D representation, so N is the number of sites and T the time here, we can observe some oscillation corresponding to the oscillation given by the theory. So this omega corresponds to the wave number of the carrier wave, and at higher order, we can observe the corrections. This is the oscillations we observe from the carrier wave. So now, if we look at for the dark soliton, this is the same concept from the bright. This is only a different solution of the analysis equations. From this, we can obtain directly the initial condition for theta and u following these two relations. By doing that, we can observe our dark soliton propagations here inside our simulations, inside our structures. The same, black is the prediction, and the blue point corresponds to the numerical simulations. what I would like to finish about this part, it's about perspective. So the idea here, we have a model which predicts which kind of parameter we need to use as initial condition to observe bright and dark angular vector soliton. But the idea is to use it to experiments. So by doing that, we need the setup. This is in the LOM, in Le Mans, which represents here all metamaterials. Here it's a granular bed to limit some viscous effect here due to the floor here. And to do that, we need to improve the model. So take into account the losses. So by doing that, we can observe from this is preliminary result for numerical simulations with losses. We can observe the bright soliton with diminished the amplitude following an exponential classical. This is some goals and some next step for my PhD. So let me finish with a final effect called extreme wave event, and more especially gradient catastrophe, to observe some things interesting in our structures. What is that is called gradient catastrophe. And gradient catastrophe and Peregrine soliton is directly linked with rogue wave or extreme wave events. Some of you know what is rogue wave? No? So, oui. It's l'accélérateur en français. This is a giant wave which emerged seemingly from nowhere, throwing over surrounding waves. So that means this is a mystical event. Until now, and already, we don't know really what kind of phenomenon can bring this kind of event. This is a giant wave, it can emerge. We don't know how in the ocean. And this is very interesting to know, because it's a it's a big trouble for ship and the industry in general. So the characteristic of this kind of wave, they are from high amplitude, stiff wavefront profile, rare, and localized both in time and space. So these kind of events are really treated for maritime safety and infrastructure. So for example, some accident from this kind of events. So this is an offshore platform. This is a ship here. And this is a picture of, I don't know if we see very well, but this is a wall of water from 20 meters. Between 1995 and 1999, there is a lot of shipping destruction and accidents around the globe here of this kind of event. And the question is, what physical system could bring this kind of wave? And one answer, of course, is the nonlinear Schrödinger equations on the oceans. And there is a theory called the gradient catastrophe, which brings some object called Peregrine soliton. This Peregrine soliton, this is a mathematical object, depending in the space, localized both in time and space, which has been chosen to be one mathematical object to represent a rogue waves. Because from the shape, you don't see very well, but there is some hole here around it, and here a big amplitude. And the characteristic from this object follow the description of what is a rogue wave. There are different mechanisms we can bring this kind of object, as we observe here with the random perturbation, looks like to modulation stabilities, what we observed before, or a current pulse, for example, here we will observe directly. So initially we have a giant pulse, very large in space, and due to the property of the medium, we can observe a localization and the generation of this kind of structures. So in the semiclassical limit of the NS equation, so that means when n here is very big, we have the nonlinearity much bigger than the displacements. And due to the large initial hump, what we can observe here, the pulse, this pulse, during the propagation is primarily influenced by the nonlinear effect. And due to this nonlinear effect, we have a self-steepening of this larger pulse. And at a critical point, we have the gradient catastrophe phenomenon apparitions, and these regulations will appear some Peregrine soliton, like this one. So from the theory developed by Bertola and Tolvis in 2012, we can predict the point, both in time and space, when this kind of event can appear. we can predict it. So the idea is from the theory developed by Bertola and Tolvis, we can use it in our effective analysis equations, what we have developed during my theory with my P and Q, to observe this kind of event in FlexM. By a change of variable, we can write the analysis equation with P and Q with only this n, this is called the soliton number, and apply initial conditions, which is relatively simple. It's a large pulse. We use a Gaussian. This is a random Gaussian. It's only a large Gaussian. We have not really matter about the width. If it's sufficiently large in comparison of the size of the Peregrine, we can observe the generation of Peregrine soliton. And following the theory, we can also obtain initial condition for the longitudinal displacement. And if we observe the result, the numerical result, we observe here n corresponding to the number of cycles and c the time. We can predict it's the apparition of the Peregrine soliton. And if we look the analysis simulations, so the direct simulation of the nonlinear equations, the Peregrine soliton, the object, and our FlexM, it matches pretty well. And the same for the longitudinal displacements. And we can observe this famous Christmas tree. The question is, for perspective, is can you use these extreme events, so gradient catastrophe, in FlexM to observe some things interesting and useful? Because it's more theoretical, can we observe some things very nice? The idea is in the ANER project, in collaboration between the LOM and SUBMECA, is to use this kind of emergence of gradient catastrophe in bistable system. So bistable system consists in a structure. This is a picture just here. This is here a mass spring systems here where the mass are linked by beams here. Bistable system means there is two shapes. So in one stable state here, all the particles are on the left, and the second one, all the particles are on the right. If from a state one we have sufficiently amount of energy, we can have a transitions of all the particles in the right direction. So the idea here, initially, from state one, this is the simulations here, we have all the particles on the left directions, but due to the generation of the gradient catastrophe, we can choose the positions, which kind of cell will trigger the transition. So we can control this one. So here, if the energy are sufficiently high for this particle to go to the potential barrier here, this particle can go in the second potential well towards the transition. So here we have the carrier wave, and after the critical point, we will have the gradient catastrophe apparitions and the generation of the Peregrine soliton. And the generation of the Peregrine soliton will trigger the transition wave. Here, if we summarize the result, here we have initially, this is the evolution of time of the dynamic of the particle at the middle of the chain here, of the bistable systems. They're oscillating due to the carrier wave, but after a moment, the gradient catastrophe appearing and the Peregrine soliton too. So in black correspond to the theoretical Peregrine soliton, and we can observe here the emergence of the Peregrine soliton will trigger a large amount of energy. So this is a conservative system, so that means this particle take the energy of all around particles to generate this kind of structure, Peregrine soliton, and trigger the transition wave. And due to coupling between the particles, there is a transition between all the particles here. So in conclusion, this PhD work has been dedicated to theoretical and numerical investigation of propagating modulated wave in FlexM. And starting from a discrete nonlinear model, we have found an analytical model to model the envelope of modulated wave inside these structures. And thanks to numerical integration of the equation of motions, we have found that our analytical model is pretty good to observe some effect of the analysis equations. We have also analyzed the effect of the 2 degrees of freedom on the geometry, on the stabilizations of the systems, and we have observed a plethora of phenomena. So thank you for your attention.
Well, thank you. If you have any questions, please ask them.
Applicative. Not yet, not yet. The idea about this back stability, this is the most
targeted one.
targeted one. Is about more soft robotics. As I mean, example is to control, because by controlling here the focalization of energy, for example, we can build some structure able to move as we want by exciting from one edge, for example. We can trick some displacement of structure and more soft things, yes. But it's very theoretical work, yes.
Okay. So if you have more questions, maybe we can finish this session. And thank you.
Thank you.